Hi everyone, welcome to Mrs. Fiorella's lesson 9.8 Pythagorean Theorem and Space Figures. I hope that you all enjoy your e-learning day today. So when we talk about space figures, we're really talking about 3D figures. And two figures that show up pretty regularly are regular or rectangular solids or regular square pyramids. Couple of things. In a rectangular solid, we talk about having a face. So a rectangular solid is made up of all rectangles here, kind of like a Kleenex box. So this figure, this rectangle ABFE, would be considered a face. So in a rectangular solid, we have 6 rectangular faces. And we talk about this segment AB. Segment AB down here at the bottom, that's referred to as an edge. So where you would have two of your faces meet, segment FG or GC, any of these segments are considered edges. So in this figure, we have 12 edges. And then we also talk about a diagonal. Now, a diagonal of a figure is going to start here, like in this back, and start at H and go through the solid to B. So the diagonal actually cuts through the entire solid while the faces and edges are on the outside, around the perimeter. The second kind of figure we talk about, this square pyramid, and we refer to it as a square pyramid because we look at this figure on the bottom, JKMO, and even though on my picture it looks kind of like a rhombus, that is the base and it is a square. So we name a pyramid by the shape of its base. Base is a square, this is a square pyramid. Up top, we call this point P the vertex of our pyramid. And then we have something called an altitude. And just like we have an altitude in a rectangle or a triangle, an altitude starts up here at the vertex and it drops down into the center of the pyramid perpendicular to that base. So this segment PR is referred to as the altitude of the pyramid, and it's perpendicular to the base and hits the base at its center. So point R is the center of that square. One more kind of figure that we have here, we have something that we call a slant height. So segment PS is what we call the slant height. Oops, H-E-I-G-H-T, the slant height of the pyramid. And I think about it like, if you could picture being able to walk up the outside of this pyramid, you'd walk on the outside triangle there. That's your slant height. Now, I want you to see that there's a right triangle hiding in there. That triangle PRS is a right triangle, so we're going to need Pythagorean theorem in these kinds of problems. Last little note down here says a cube is a rectangular solid in which all edges are congruent. You think of a Rubik's Cube, you think about a die that you roll, a 6-sided die. Cube, 6 squares, 6 square faces. So next, I have a little note here that says, right triangles hide in polyhedra. Polyhedra is the fancy word for these 3D solids. So this is great practice of our Pythagorean theorem and our special right triangles. We will see more of these in chapter 12, but we want to get your connection here with right triangles and Pythagorean theorem. So our first example, given the length of segment AB, when we don't write the hat, right? We don't put the hat on here. That means we're talking about a length. AB has a length of 4, so I'm going to put this 4 in here. So this segment AB is 4, and segment BC, how tall this rectangular solid is 12, and segment BF over here is 3. So I want to remind you that this is a rectangular solid. So this base down here is a rectangle. That means I could put a little right angle in here. I know it doesn't really look like it, but we have this right triangle. And I'm hoping that you guys are remembering from all of those, the Pythagorean triples that we talked about. Maybe if you don't know me, you don't know that this is my favorite triangle. 3, 4, and 5. So that segment FA, this is a diagonal of that face, is a 5, length of 5. Now, I want to point out that there's another right triangle that's hiding in here. Segment GF, segment FA, and then this diagonal GA. So if I kind of look at this, here's what I'm looking at. I'm looking at this triangle, GFA. Now, my bases of my rectangular solid are parallel to one another. So I'm thinking when I look at this segment GF is going to be perpendicular to that base. I have a little right angle in here. I can draw a right angle in there. I know it doesn't look like it because we have a 3D picture on a flat surface. So I'm also seeing this length CB is 12. All of these segments are going to be congruent. So that GF is also 12. So now I have this segment 12 and this segment 5, and I'm hoping you recognize another triple. 5, 12, 13. Now I just suggested we were going to need Pythagorean theorem. However, we use these special right triangles, these triples. So we got our diagonal, segment GA, I didn't mean to write that in laser pointer. Segment AGGA is length of 13. Now the next questions say, we've got to find D in simplest radical form. So we're going to find the diagonal, and it looks to me like all the sides of this figure are 1. So this isn't just a rectangular solid, this is a cube. All those faces happen to be squares. So what if I look at this, if I look at one of these bases or one of these faces, this is a square. We got this square, and we have a diagonal going through our square. Now we've learned in the last couple days, we talked about hiding in a square is a 45, 45, 90 triangle. So we have this little right angle in here. Our pattern for this is that we would have x, x, x root 2. So this diagonal is actually going to be 1 root 2. So now, kind of like the last question, we have another right triangle hiding in this picture. I can see this right triangle here. It's got one side of 1 and one side of root 2. So if you're having trouble seeing it, you can draw it separately. So I have a 1 and I have a root 2 and I have this diagonal. If I do Pythagorean theorem, 1 squared plus the square root of 2 squared equals d squared, I'm going to get 1 plus 2 equals d squared. 3 is d squared. So that diagonal has a length of the square root of 3. Square root of 3. Now what would happen if we tried this and the cube had a length of 2? So we still have this little right triangle hiding in here. It's another 45, 45, 90 triangle. 2, 2, 2 root 2, right? My 2's are all around. So if I were to redraw this triangle, what I'm noticing I'm going to have is a 2. Oh, I'm sorry, I put my 2 in the wrong spot. A 2 root 2, right? I'm looking at this right triangle with the diagonal as the hypotenuse. Okay, I'm thinking I want to use reduction. If I divide both of these by 2, I have the lengths of 1 and the square root of 2. You guys, we just did the Pythagorean theorem using that information. We don't have to do that again. We're going to get the square root of 3 for our answer, but we have to remember that we divided by this 2. So this is 2 root 3. My diagonal has a length of 2 root 3. Do we see a pattern? What if all of our sides were of length 5, 5, 5? We would have a diagonal length of 5 root 3. So if I have my side lengths of S, S, and S, I'm betting you can deduce that this diagonal length is going to be S root 3. What I'd really like you to do now is pause the video and try these last few problems. So pause the video, try the couple problems, and then you can check your answers. So you can check your answers, you can fast forward through, and I feel like you're going to catch on to this great. Once you finish, you will work on your homework in your packet. So you'll find your packet that's 9.7 to 9.9, 9.10, and you'll work on the homework for 9.8. So pause your video now, try problems 3 through 6. Okay, welcome back, ladies and gentlemen. So when you do this, I'm hoping that you recognize down here we have a 6, 8, 10 triangle, and I'm looking and I'm seeing these heights of this figure, this cube, are also 10. So if I were to draw the triangle I'm looking at, I see 10, 10. I'm hoping we recognize this. This is 10 root 2. If you didn't recognize it, you could use your reduction method and you could do the Pythagorean theorem. Question 4, the base of a regular square pyramid is 1,600 square units. So if my base, this is a square, my side squared is 1,600. If I take the square root here, that means the side length of my base is 40. So I have this square, 40, 40, all the way around the bottom of my base. So it says the triangular faces are equilateral triangles. So this triangle right here is equilateral, which means if the base is 40, I also have 40 for each of these segments, 40 for the other sides. Find the slant height and altitude. So we have two problems to work on here. So what I'm thinking is the first thing I'm going to concentrate on is this face. I have an equilateral triangle. Here's my equilateral triangle. Well, I'm going to make that look more equilateral here. I've got 40, 40, and down on the bottom is 40. My slant height, a lot of the times we use the letter L for slant height, right? So we don't want to get that confused with the altitude or the height. This base is going to be divided into 20 and 20. So now I'm thinking, in my equilateral triangle hides two 30, 60, 90 triangles. So I'm noticing across from my side 30 is that 20, that's the x. Across from the 90 is the 2x. Across from the 60 should be the x root 3, 20 root 3. So the slant height is 20 root 3. Now we also want to find the altitude of this pyramid, so we're going to have a secondary triangle in here. We have another right triangle right there. So what I'm looking at is I'm going to draw that second right triangle. I've got the height or the altitude that I want to find, and now halfway across this pyramid's base is going to be 20. So I have a 20, and now that slant height, we just found this length. That is 20 root 3. So if I do some reduction, if I divide these both by 20, I get a 1 and a root 3. So 1 squared plus h squared equals the square root of 3 squared, right? 1 plus h squared is 3. H squared is 2. And when I take the square root, I get square root of 2. But remember, it's not just square root of 2. I divided by a 20. 20 square root of 2. So the altitude is 20 root 3. Okay, two more questions to finish up. A regular square pyramid has a slant height of length 26. Here's my slant height, length 26. All right, the altitude is of length 24. So that's down here in the middle, 24. And then it says, find the length of the diagonal of the base of the pyramid. That is not even drawn in my picture. So before I do anything, I'm going to concentrate on this right triangle here. I have this right triangle that's formed by the slant height and the altitude. So slant height is 26, altitude is 24, and I'm going to call this x down here, right? That's this side down here, halfway across the base. Thinking about when I look at this, both of these are divisible by 2, 12 and 13. You guys, 5, 12, 13. But it's not just 5 because we divided by 2. This length is 10. That means all the way across my base is 20, right? 20 all the way across my base. If I want the diagonal of my base, I'm looking for the length of the diagonal of this square. 20 by 20, I want this length. And if I draw that in my picture, it's going to go across here. 20, 20, and we have that little right angle in there. The right angle. We have a special right triangle hiding in here. 45, 45, 90. X, x, x root 2. So that diagonal's length is 20 root 2. Last question. Segment BF has a length of 9. Segment BA has a length of 12. And segment GF in the back there, GF, has a length of 8. So this kind of goes back to one of the first problems that we did together. I have this base, It's a rectangle. 9, 12, and then we have this diagonal. 9, 12. You guys, divide by 3. 3, 4, 5. But I don't want just 5. 5 times 3 is 15. So my diagonal FA is 15. Now I'm going to highlight this triangle, GFA. So I'm looking at a triangle that looks like this, my right triangle here. GFA, I have a length of 8, 15, and I know that you guys are thinking in your head, 17, Fiorella. Segment AG has a length of 17. I didn't even need a Pythagorean theorem there. So what I'd really like you to do now is I would love for you to work on your homework from 9.8. Good luck, ladies and gentlemen, and I hope you enjoyed your day.